The 3' end of the primer is positioned in the polymerase active site to allow addition of nucleotides to this end. During elongation, the replication bubble gets bigger as the helicases move apart, establishing two replication forks that move in opposite directions. The sliding clamp and polymerase unit at each replication fork moves along the DNA as the helicase unwinds the double-stranded DNA to expose single strands. Let's focus on just the right-hand fork for the moment, as the processes at both forks are identical. Polymerases are loaded onto both the top and the bottom DNA strands at the fork. Because polymerases only synthesize DNA in the 5' to 3' direction, the two strands must be copied in opposite directions. The bottom strand in this fork is the leading strand. The polymerase on this strand moves continuously from left to right, synthesizing DNA as it travels. The top strand is the lagging strand, on which just a short stretch of DNA is made by the polymerase elongating in the 5' to 3' direction. After synthesizing this short stretch of DNA, the polymerase then dissociates and a new polymerase binds at the fork to elongate the next RNA primer. So priming and elongation are happening repeatedly on the lagging strand as the replication fork moves along the DNA. Synthesis is discontinuous. The short stretches of DNA that are made on the lagging strand are called Okazaki fragments after their discoverer. During the course of replication, these fragments are stitched together. When the lagging strand polymerase runs up against a previously made Okazaki fragment while in the process of synthesizing DNA, the replicative DNA polymerase 3 is replaced by DNA polymerase 1, which has 5' to 3' exonuclease activity. This exonuclease then degrades the RNA primer in front of it, synthesizing DNA as it goes. Once the RNA primer is removed, the two sections of DNA are joined by DNA ligase. Now the lagging strand has been elongated by one more Okazaki fragment.